Hello everyone. Today we'll be looking at some quick solutions of All India Akash Test Series JEE Advanced 2019 Test 3A Paper 1 Code A and B. So let's start with the first section. This section contains 6 questions. Each question has 4 options out of which only one option is correct. So let's start with question number 21. So in this question we have been given 3 molecules A, B and C, and the examiner seems to be interested in the site of protonation in this molecule. So let's start with the molecule given in option A. So students, we know that the protonation site should be the most basic site in the molecule, and the basic nature depends upon the stabilization of the conjugate acid. So in molecule A, we can see that there are 2 competing sites, the lone pairs over oxygen and the lone pairs over nitrogen. Now let us try and form the conjugate acids of both of these structures and compare their stabilities. So let us assume that the protonation takes place at the oxygen. So there will be an H added to the oxygen, and oxygen will bear a positive charge. So this is the structure when the lone pairs over oxygen get protonated. Now let us see what happens when the lone pairs over nitrogen get protonated. So we'll have CH3CO NH3 and the N will bear a positive charge. Now if we look at these 2 structures, we can clearly see that the lone pairs over nitrogen will be in conjugation with the double bond, and which will lead to the stabilization of the oxonium ion which was formed. Okay, so we can say that this site is more basic as the conjugate acid is resonance stabilized. So in the molecule given in A, the protonation shall occur at the oxygen. Let us look at the molecule given in option B. So we have 2 sites. One is the cyclic nitrogen and the other is the nitrogen which is outside the ring. So here again we have 2 competing sites. There are lone pairs on the cyclic N as well as the aliphatic N. So let us first try and protonate this nitrogen. So we'll have this ion which is not resonance stabilized, and on the other hand if we try and protonate the cyclic N, we'll have the structure. And as we can see that the lone pairs of this nitrogen can stabilize the conjugate acid. So students, in this molecule, the cyclic nitrogen is more basic and protonation should occur there. So let us try and look at the molecule given in option C. So we have 2 competing sites. One is nitrogen and the other is carbon. So if the protonation occurs at carbon, we'll have an electron deficient nitrogen atom which will not be formed. On the other hand, if the protonation takes place at the nitrogen, we'll get this structure, and the carbocation so formed can be stabilized by the lone pairs present over the nitrogen atom. So in this structure, the nitrogen is going to just bear a formal charge, where in this structure, the nitrogen is actually getting electron deficient. So students, the more basic site in this structure is the nitrogen atom. So if we look at the options, let us look at S1. In molecule A, the protonation occurs at oxygen. Yes students, this statement is correct. Let us look at statement 2. In molecule B, the protonation occurs at nitrogen of NH2. So this statement is incorrect. The protonation occurs at the cyclic nitrogen. Let us look at statement 3. In molecule C, the protonation occurs at nitrogen. This statement is also correct, students. Let us look at statement 4. In molecule A, the protonation occurs at nitrogen. This statement was incorrect, as we had already seen before. And in statement 5, in molecule B, the protonation occurs at nitrogen of pyridine, which is the cyclic nitrogen present. So students, this statement is also correct. So if we look at the options, we can see that we have to mark option C as the correct answer to our question. Let us look at the next question. Question number 22. Carboxamides are the compound which contain this group. So carboxamide undergoes alkaline hydrolysis, and 2 experiments were done to measure the rate of alkaline hydrolysis of carboxamides. So in experiment 1, we had compound P and Q undergoing alkaline hydrolysis, whereas in experiment 2, we had compound R and compound S undergoing alkaline hydrolysis. So students, we know that during the hydrolysis, the attack of OH minus ions takes place at the carbonyl carbon. So greater the electrophilic nature of the carbonyl carbon, greater will be the rate of the reaction. So the lone pairs of nitrogen appear to be conjugated with the carbonyl group present. But we can see that in the compound P, the resonance will not be very effective. As this molecule will be highly strained. So this resonance is not very effective, whereas in the compound Q, the resonance can take place relatively easier. So because of this resonance, the electrophilic nature of this carbonyl carbon shall decrease, whereas no such resonance is taking place in the compound P. So in compound P, the carbonyl carbon is more electrophilic. So the rate of hydrolysis of compound P shall be greater than the rate of compound Q. Let us look at the compounds R and S. So we can see that in compound R, the resonance will also be again not very effective, as the nitrogen is a bridgehead nitrogen. Okay. While no such thing is happening in the compound S, where the lone pairs of nitrogen can easily be conjugated with the carbonyl group and thus reduce the electrophilic nature of this carbonyl carbon. So we can see that due to resonance, the compound S will undergo alkaline hydrolysis at a relatively lesser rate than compound R. So this was the ease of hydrolysis of these compounds. So P is more readily hydrolyzed than Q, whereas R is more readily hydrolyzed than S. So looking at the options, we can see that the correct statement is given in option C. Let us look at the next question. Question 23. Different structural factors lead to the special stabilization of the enol form. The enol content is compared with the help of equilibrium constant K of tautomerism. Okay. So we have been given 5 compounds and we have to comment on the equilibrium constant of tautomerism between keto and the enol forms. So it is already mentioned to us that the K is represented by concentration of the enol form to the concentration of the keto form. So the examiner just seems to be interested in knowing in which species the enol form is a major contributor to the equilibrium mixture. So if we look at option P, Q and R. So P, Q and R are just positional isomers of each other. So if we look at the tautomer of the structure given in option P. So we can have the enol form, as this. And students, we can see that this enol form is stabilized by hydrogen bonding. So if we look at option P, option Q and option R, so the enol content of P will be more than the enol content of Q and R, as no such intramolecular hydrogen bonding is going to take place in molecules Q and R. So we can say that K1, which was the equilibrium constant for the structure P, is more than K2 and K3, which are respectively for Q and R. So K1 is more than K2 and K3. Okay. If we look at option S and option T, so if we draw the tautomer of molecule T, we have this structure. And if we look at the tautomer of molecule S, we have this structure. So if we compare these two structures, we can see that the enol form of T is more stable as there is an extended conjugation. So we'll have K5 greater than K4. So if you look at the options, we have to select the incorrect relation between these equilibrium constants. So if we look at the options, K1 is greater than K2, the statement is correct. K1 is greater than K3, it's correct. K5 is greater than K4, this statement is also correct, students. So the incorrect relation among these must be the fourth option, as we have already seen that K5 is greater than K4 due to extended conjugation. So students, we have to mark option D as the correct answer to our question. Let us look at question number 24 now. Ethyl acetoacetate on reaction with methyl vinyl ketone in presence of ETONA forms cross product which on heating forms a cyclic compound P. So the compound P is further subjected to reactions where it forms Q, and we have to comment on the structure of Q. So let's first try and figure out what the compound P is. So it is formed by the reaction of ethyl acetoacetate and methyl vinyl ketone. So if you draw the structures, so ethyl acetoacetate has an active methylene group and we have a methyl vinyl ketone. And this is subjected to reaction with ETO minus. Students, the ETO minus is a strong base and it is going to extract the hydrogen present on the active methylene. So it is going to generate a carbanion. That carbanion is resonance stabilized by two carbonyl groups. So this nucleophile thus generated will attack on the compound given below, as the examiner seems to be interested in the cross product formed by the reaction of these two. So students, we have a conjugated system, alpha beta unsaturated carbonyl compound, and this nucleophile generated will give a 1,4 addition product with this substrate. So it is going to attack here and the product form will be a 1,4 addition product. So we'll have this structure. Now students, it is mentioned to us that ETO minus is present in excess. So this ETO minus is going to extract this acidic hydrogen and the carbanion thus generated shall attack on the ketone group present. So it will attack over here. Another alternative was to attack on the ester, but we know that the ester is not very available for attack as compared to the ketone because of lesser electrophilic nature of the carbonyl carbon. So it is going to form a 6-membered structure. Let us try and draw that structure. So we have a 6-membered ring and we have a ketone in the ring. The attack is happening here, OH, CH3, and adjacent to that we have an ester group present. So this on heating shall lose a water molecule and lead to formation of the compound P, which is this. Now students, this is the compound P. Now this compound P is subjected to catalytic hydrogenation. So this catalytic hydrogenation is going to convert the ketone into alcohol. It is going to remove the double bond. It is going to convert this ester into an alcohol again. So let's try and draw the structure. So we had the compound P as this. Okay. And when it is subjected to catalytic hydrogenation, we are going to have this. Let's call it as structure X. As we had seen, the double bond shall be removed and this ester shall be converted into an alcohol. So next it is subjected to reaction with H2SO4 heat. So H plus heat is going to remove the alcohols and convert them into alkene. So the carbocation generated here shall migrate inside the ring and form an endocyclic alkene. So this structure will be formed, and then further when it is subjected to catalytic hydrogenation, we are going to have 1,2 dimethyl cyclohexane as the major product. So if we look at the options, we have the correct structure of Q given in option B. So we have to mark option B as the correct answer to our question. Let us look at the next question. Question number 25. Baeyer-Villiger oxidation contains ketone into an ester and a cyclic ketone into a lactone. Consider the given reaction. So we have benzophenone, in which the oxygen of benzophenone is labeled, and it is allowed to react with peroxyacetic acid followed by acidification. So we have a product P, which is the major organic product, and now the examiner is interested in knowing about the location of the labeled oxygen in the product. So if we look at the mechanism of this reaction, so in the first step, the H plus will go and protonate this labeled oxygen, so which will create an oxonium ion, which will lead to an increase in the electrophilicity of this carbonyl carbon. So now the nucleophile can attack here. We have pH, COH, and pH. And the nucleophile will be peroxyacetate ion, CH3, COO negative, which can now attack this carbonyl carbon easily. So we are going to have the pi bond shifting over oxygen. So in the structure formed will be this. Now students, we have a good leaving group present in the form of acetate ion. So what will happen is this pH will attack on this oxygen and this leaving group shall leave. So there will be a migration of pH group onto the oxygen of the peroxyacetate ion. So we'll have pH So let us just follow the labeled oxygen. So we have this oxygen was labeled, this will be labeled, and this will be labeled. So now, due to the formation of carbocation, these lone pairs over this oxygen shall attack, which will lead to the formation of the ester. After deprotonation, and the labeled oxygen will be retained. So if we look at the options, we can see that the correct structure is given in option B. So we have to mark option B as the correct answer to question number 25. Let us look at question number 26 now. Consider the following reactions. So we have been given the substrates as cis-2-butene and trans-2-butene, which are symmetric substrates. And we have reagents. There is osmium tetraoxide, there is MCPBA followed by hydrolysis. There is Bayer's reagent, which is nothing but cold KMnO4. So students, if we look at the reagents, we know that osmium tetraoxide and Bayer's reagent, they both lead to syn hydroxylation. They both cause addition of two OH groups in a syn fashion. And if we look at MCPBA followed by hydrolysis, so what this MCPBA? So this MCPBA is nothing but metachloroperoxybenzoic acid. So it will lead to formation of an oxirane, and that oxirane will be further hydrolyzed, leading to the formation of a glycol. So students, this MCPBA followed by hydrolysis is leading to trans hydroxylation. So the addition is trans addition. Now students, we know that trans compound plus anti-addition will give us a meso species, whereas cis compound with syn hydroxylation will lead us to meso species again. While the other two combinations will give us a racemic mixture as the major product mixture. So we have a cis compound undergoing syn hydroxylation. So cis plus syn addition will lead to the formation of a meso compound. So will a trans with an anti-addition. So if we look at all these reactions, we have reaction 4 in which a trans compound is allowed to undergo anti-addition. So this will also lead to the formation of a meso compound, while the other two reactions, cis plus anti-addition, will lead to racemic mixture, whereas trans plus syn addition will also lead to a racemic mixture. the compound form in all of these cases will be butane 2,3 diol. So let us look at the options. The examiners seem to be interested in knowing about the incorrect statement. So option A, compound P and compound R are diastereomers. Compound P is a meso compound, whereas compound R is a racemic mixture of the optical diols. So this statement is correct. These are diastereomers. Looking at option B, compound P and compound S are identical compound. Yes, both of them are meso, and the meso form of butane 2,3 diol is this, and both will lead to the formation of this species. So statement B is also correct. Let us look at option C. Compound Q and compound R are meso compound. This statement is incorrect, students. Compound Q and compound R will be an equimolar mixture of the optically active diols. So both Q and R will have an equimolar mixture of these two compounds. And these are PNS. So statement C is incorrect. If we look at the D option, compound S is optically inactive. This statement is correct. Compound S is a meso compound, so it shall be optically inactive. So we have to mark the incorrect statement for this question. So the correct answer to our question is option C. Let us look at the next section.